Okay, so I think we can start. I know people are still getting food, so we'll get started. And by the time I'm done with the introductions, I think everyone will be sitting down. Welcome to the first of this year's seminars under the UTC Institute for Advanced Systems Engineering. Just a couple of things for the participants, audience first. I think most of you are from UConn, so you know where the exits are. For the few people outside of UConn, in case of an emergency, you can take the stairwell downstairs, and then there will be exits to your right and left. In terms of the other logistics, there is an attendance sheet. Is that going around? Yep. So please make sure that you put your name and an email address and an affiliation there. And the other thing we are doing is collecting feedback from the participants in terms of the arrangements. One arrangement that you can note is the technical difficulties with the presentation initially. But we are looking for your feedback in terms of the topics and seminars and how you like this topic, and for the future also the relevance of the speakers and the topics to systems engineering that we are trying to promote. So that if you don't have those forms, they are on this table. You can collect them or we can circulate it. So please do fill that out, and we'll collect those forms at the end. And the same thing with the attendance sheet. There should be 2 or 3 attendance sheets going around. So if you don't get to one, there should be another one going around. With that, it's my pleasure to introduce today's speaker, Richard Poisson from United Technologies Aerospace Systems. He's been with UTAS for more than 30 years. I've worked with him on a few projects, so I could read the bio that was in the announcement. You can read the announcement yourself, so I'm not going to repeat things there. But I've worked on a couple of projects with Rich, and I've always been very impressed with his breadth of knowledge and breadth of experience. He's worked across different disciplines, electrical engineering, mechanical engineering, computer software, systems modeling, and it is amazing how much he knows about all the different subjects that we cover in systems engineering. And today he's going to talk about fault detection. So he's going to, you are going to take questions in the presentation also, but we'll try to leave 5-10 minutes at the end also, so that you can participate. And then also we'll stick around after the seminar if you want to discuss more informally different topics with him or other UTC folks here. Rich?
Thank you, Doctor. Thanks, everybody. It's more of a filled house than I expected. When I was first asked to give a seminar, I thought this was great. I had something I had done for mechanical engineering on efficiency in 2013, and I figured I could dust it off, update it, because efficiency still matters. But then our IT department lost my presentation. And I was actually glad, because it got me an opportunity to do something different. And fault detection and fault isolation is becoming probably one of the biggest things we have to deal with every day. It is a difficult topic. In some areas it's actually quite simple. In some areas it's almost impossible. So that's why I want to talk to you about understanding what happens in the fault detection world. For those of you not in aerospace, it's very regimented, but there are opportunities where we can bridge some technology gaps, and we'll go through those. So the key ideas is we build mechanical things. Everything fails. Everything falls. They're always going to be there. Everything we build is built on safety, so everything that flies has to be safe. Fault detection and isolation is a key part of that. Why is it hard? No one wants to carry extra equipment on an airplane because it weighs a lot. So detecting with what you have is very difficult. built-in test, we'll get more on that, is also very important because false alarm rates, things that you flag that are errors that are not really errors, annoy people. You don't want a delay in cancellation because a light went on in the cockpit when there's really nothing wrong. The no fault found. We've flagged something, we've taken it off the airplane, we bring it back to the facility and test it, and it's perfectly fine. We just made a cycle, we've just annoyed a whole bunch of people. And really what's happened is we are still working on a component level fault detection isolation methodology. And really what happened is the interaction that is now in place with the highly integrated aircraft has basically, we've reached the plateau in what we can detect without some new methods and new tools and new thinking, to be honest with you. So that's things I want you to take away from today. And we'll go through some of the things. So I've divided it into a few parts, and we'll go through, just for people who have not worked in aerospace, what the difference is on a fault, a hazard, and a failure, because they are technically different terms. Hazards. These are things that you do not want to see. These are things like the engine not running, the air conditioning system not running. These are hazards. These are things that make flight hazardous by definition. And in the aircraft world, we've categorized those from minor to catastrophic. Catastrophic is loss of airplane. Minor is the pilot might have to do some extra work. That's really all there is. And they're classified by probability, the likelihood. Catastrophic things we don't want them to happen regularly, so the number comes out to be somewhere in the neighborhood of 10 to the minus 9, so one failure every billion hours of flight. And severity, that's the minor, major, hazardous, and catastrophic. This is all done at a top-down level. A fault is not necessarily a bad thing. It is an anomaly that happens under normal operation. The problem with a fault that if it's left untreated, it reaches a failure. A failure is an inability to perform the function. That's the key part, because what we do is we provide functionality. So if you don't handle the fault, recognize it, accommodate it, and isolate it, you're going to get to a failure. And once you've realized the failure, you may be in a hazardous situation. Think about the tire. Tire with a nail in it. If it's leaking air, it's annoying, but it's not a problem yet. If you get to a flat, that's a problem. So a fault is something that occurs that's anomalous, that you care about, but it might not lead to a failure if you take correct steps. So why do we care? In aerospace, anything that is put on an airplane as equipment has to be safe, and it has to add value. When I mean adding value, it's a term that is bandied around a lot. We don't carry stuff for no reason. Even the coffee maker is there for a purpose, to provide you comfort while you fly. Same with the entertainment system. It adds value. It makes the plane more, makes you want to fly more, makes the plane more saleable. But it also has to be safe. Fault detection or failures detract from both of these. If you've ever in an airplane and your little seat back DVD doesn't work, or you're delayed because there's a light on in the cockpit, these are things that annoy people, and this is what we try and get rid of. So how do we do this? This is done through all parts of a design process in aerospace. We have from the requirements, and we'll talk about requirements a little bit, through the design and test. And we always are doing things like hazard analysis, safety analysis, failure modes and effects analysis, and failure modes and effect component analysis. These are the tools that we use in different stages to identify the faults that can happen, how to identify when it does, which fault it is, how to isolate it, and then in some cases, how to accommodate it. So it is really a top-down process. And because of that, you start at the very beginning with grand hazards. Shall not have the engine shut down. Shall have the landing gear brakes always work. Things like that. And you get down to the subcomponent level, like what happens if a bearing in a compressor goes. How do you handle that? It's a very, very regimented process. There are a lot of technical specifications in the aircraft world. ARP 4761 is the method for doing the safety assessment. So they not only tell you you have to do it, they tell you what's an acceptable way of doing it for certification. So again, aerospace industry is very standardized. It has to be so that we always get safe and consistent flight. In terms of the complete aircraft, the aircraft is divided into FAA ATA chapters. Chapter 28 covers fuel systems. Chapter 24 is the electrical power generation. There are 92 chapters for building an airplane. These are just two of them that we work with all the time here. So in addition to getting the specification from your customer saying, I want to build an airplane that houses, that can carry 150 people, you also have to look at Chapter 21 and say, what does that mean? That will describe some of the predetermined hazards that you have to accommodate, their severity, and then you look at your system and find out that you meet those. There are general purpose specs that we always deal with. Again, aircraft industry is spec driven. We are very specific in our specifications. ARP 4754A is how you do the design. This is a kind of like the systems Bible. Decomposition, validation of requirements, verification, testing, and all of that. 4761 is, like I said, the method that you do when you do an assessment for safety and hazards. These two are low-level components. One is for software, DL178. It's software considerations. It's basically a how-to for software. And the new one, the latest one, is DO254, which is basically the design assurance guideline for hardware, basically validation and independence for hardware design. But these are the type of specs. There are many more. We have EMI, we have vibration, we have certain specific tests on your chapters. So how do we do this? Okay, now here's the commercial for UTC. This is the new 787. It's really not new anymore. It's been flying for a few years. But if you look at the breadth of systems that we have on there, we have the nacelles, which are here, thrust reverser, primary power distribution, cabin air control, we have the gearbox, we have interior lighting, we have fuel management, we have braking, we have fire protection. This is everything we build on this airplane, one airplane. And in a lot of cases, we have the same content, slightly skewed for different ones. So there's my UTC commercial. Shows you that we have to work in a lot of areas, a lot of ATA chapters, a lot of very big systems, a lot of very small systems. So how do we do this? We start with the hazard, and we divide it into three levels: aircraft, system, and subsystem and component. And remember that everybody's system is somebody else's subcomponent. Everybody's subcomponent is their system. So you can move the abstraction layer wherever you want to start with. But we always start with the hazard analysis. What are the things that happen if you fail? And what are the ramifications to the airplane in terms of safety and in function, and how do I fix them? That's done with things like safety assessment and fault trees. There's a whole branch of science goes on in fault trees. Again, when you're at the system level, you do another analysis at your abstraction level. So you go there. Again, create fault trees. From there, you go on to components. Components are done a little differently because now you have a design and you analyze your design. What happens if component A fails? How does it fail? What's the likelihood of it failing? And then you look at the system response. That's an FMEA, failure modes effects analysis. But this is the process that we follow. It's again governed by 4761 in spirit. So if you look at the aircraft, we'll take a quick dive into the aircraft. So we have our nice new airplane, and we need an air conditioning system. So that's this guy right here, fits in the belly of the airplane. It's made up of a number of components: a compressor, a turbine, heat exchangers, some valving, and a whole bunch of other things. And you can see a simplified schematic on the left. So in terms of systems, we have the environmental control system. We have an air conditioning pack. That's what these are called, pack for package. And then we have the heat exchanger, which is this piece right here. There are 2, maybe 4 of these per airplane. Each one is pretty much identical to just different size of the airplane. And why? Because the hazard says I can't live without one of these things. This pressurizes the cabin. This keeps the temperature at the right point for human habitation. But if you look at this, this now has components. So I can lose a pack, but how do I lose it? I have heat exchangers. So if the heat exchanger fouls, the efficiency and even the operation of the heat exchanger doesn't work anymore. So I will do analysis at the airplane level. How many environmental control packs do I need? I will do it at the pack level, and I will do it at the component level. So I will do all of these analyses. It's kind of like a pyramid. You start at the system. And here's an example of a hazard. Malfunction of the air conditioning system creating excessively hot temperature inside the cabin. Well, that's the result of the failure. I can no longer control the temperature. It gets too hot. What's the hazard? It creates high supply temperature. It may shut down some of the electronics because the over temperature. It actually makes the crew, may incapacitate the crew if it's too hot. It also works if it's too cold. If it incapacitates the crew, that's a problem. So what do? We look at it. How do we verify that we've mitigated this hazard? We use fault tree analysis. We use FMEAs. We use design reviews. Because the severity that's assigned to this fault is catastrophic. Loss of airplane. Okay? So that's the first level. We do it at the system level, right? And prevention of a hazard always starts with identification and detection of faults before they turn into failure. Okay? The failure modes and effects go down one more level. Questions, comments? Am I going too fast, too slow? Good? Okay.
Now, how do you make sure that your fault trees and FMEAs are consistent?
The consistent in what way you mean consistent? That the fault tree represents or the FMEA represents the fault trees? That's done right now through reviews. Right now. There is no tool or method to link the two. It's done through reviews and a one-to-one mapping, traceability, if you will. From the subsystem point of view and the component, now that we've taken our hazard and we said we can't have high temperature, we have to look at the FMEA. And the FMEA is, like I said, the failure modes and effects analysis, where we look at the components we've chosen to design our system with. What are the components? We've used a mechanical plate fin heat exchanger. We've used a rotary compressor. We've used a butterfly valve. And we look at all of those types. And we'll look at the compressor. Right there. And we'll say, okay, what can happen to the compressor? And then we'll break the compressor down by component. The vanes, the shaft, the bearings, the housing, the flow control valve if it's in there, the diffuser. Any of the components that make up a compressor will get the same level of analysis. What can happen to it? How does it break? Is shaft shear an injury? What's the likelihood of shaft shear? What's the ramification of shaft shear? And when you look at some of these, or some complex systems, these are 1,000 pages long. They are, because every part fails in multiple ways. And when we get to electronics, it's a lot of fun also, because now you have 3,000 components in electronic circuit assembly. Every one can fail a number of ways. Circuit pin can fail open, fail short, fail indeterminate. Resistor fails open, fails short, fails out of range. So you have to analyze all of that, and what's the effect on the system at the next higher level? And what's the effect at the next higher level? So remember, we talked about going down. We do the analysis going down. But once we're down at the bottom, because we've got more clarity about how the system works, we start moving back up. We look at it going back up. This process is not a one-time deal. This is never ending. Every design cycle goes through multiple iterations where we're constantly updating the fault trees, the hazard assessments, the FMEAs, as certain things change. Now we get into software. How is the unit going to be used? So that influences what I can do. Can I recognize something? Can I do something about it? So the software also enters into this. So what do we get after we do these months and months of analysis? We get what the hazards are, how we're going to handle the hazards, whether it's redundancy or pseudo redundancy. We have all our failure modes identified. We have the probability and the severity of those, both at the subsystem and the component level. So now we know everything we know about how to prevent the faults from propagating to failures. So what do? We write requirements, because that's what aerospace engineers do. We write requirements. So from this, we write requirements that says you must detect this failure. You must be able to isolate this failure down to the component that failed. That's the problem. And sometimes that's very difficult to do. It's hard to put into words how tough fault isolation can be. You find something is anomalous, and you have to find out why, because if you don't, you have to execute, it could affect safety. You have to execute maintenance. But if you don't know what's wrong, what do you fix? And it also is, you have to understand whether you can accommodate it, living with the fault. I can live with the coffee maker out. There's this interesting concept called minimal equipment list for an airplane that says you can fly with some things not working because they're not critical to safety. And certain things are MEL'd for a certain amount of time. You can fly with certain things down for 30 days. You can fly with certain things down for 6 months. But accommodation, living with the fault, you have to know. You can't just say, it's okay, I can fly without it. If it's not identified at the fault level or the failure level, you can't do it. You have to identify. We have some really, really high standards that our customers put on us. 100%, you must identify where the fault is to within 3 LRUs, line replacement units, things that you can pull off the airplane and replace. So if you're looking at an electrical system, it could be a generator, it could be a controller, it could be a contactor. If you're looking at a fuel system, it could be a valve, it could be a pump, it could be an indicator. 3 LRUs. I have to be able to identify where the fault is to 3 pieces. It may be very hard to replace, but I still have to do it. 98% to a single LRU. So that means if I've identified it 100%, it's in my fuel system, 98% assurance that it's the valve. I have to be 98% sure that it's the valve. And if the valve is made up of subsystems, typically valves are pretty simple, but if you look at like a pack where you have compressors and heat exchanger, 95% to that. So I have to know it's the heat exchanger 95% of the time. So that's pretty difficult. So here, this we can do pretty easily. It's kind of in that system. It's pretty easy to do. This, not so easy all the time, depending on how the system is architected. That can be really tough. In the world of electronics, yes?
Is there a standard language to write these requirements?
No, it's English, if that makes a standard. But formalization of requirements is something that we are pursuing very hard. It is a key part. Models as requirements, formal, verifiable language is something that is being pursued, is not ready for prime time.
Question, why 3 LRUs?
That is just the numbers that we get. Because typically it's a controller, a feedback, and the item that you're controlling. Typically they come in 3s. That's just been their industry standard for as long as we've been in. I've been in it, yes.
What's the guidance on multiple occurrences of faults at the same time?
Don't let them happen. That's a really good point, and that's really a temporal nature of isolation too. How do the fault? Because again, the FMEA, when you do it, has no indication of when the fault occurs. Okay, so I could get 2 faults in separate subsystems at the same time. If I can identify them, good. If I can isolate them, better. If I can accommodate them, I'm good to go. The problem is that if they interact, that may be the issue. And that's really where the problems occur in terms of complexity. You've hit upon one of the key points of this seminar is complexity and interaction.
But do the ARP guidelines talk about that?
Not really, because when you do an FMEA analysis, when you do a hazard analysis, they are single event hazards at single time. Okay, I can detect and isolate this, and then I can detect and isolate that. If there is interaction, that's a common mode effect, and we have to deal with that separately. And that's where a lot of the science doesn't work well right now.
Also, people they really don't know how to compute those numbers too.
No.
Even in terms of testability, if you have, say, 30,000 components, how many possible things you'll have?
Yeah.
So you'll be dead before you get anything. So they focus primarily on one or none.
Yeah. So as you looked at the picture of the 787, you looked at how much content we have on that airplane. There are other people who have content too. It's not just us. Airplanes are more intelligent than they've ever been. They are doing more of the work of the pilot than they've ever done before. Some airplanes right now, you don't even stand on the brakes when you land. You say how long you want the roll to be, and you dial it in on a knob in the airplane. Applies the right amount of braking to follow the center line, and it stops right on that foot mark. That's how well they work. The other thing is, as we start talking about complex airplane, the causal relationships between interacting systems is not as crisp as it was before. When I had an air management system that took bleed air off the engine, I didn't care what the electrical system did. I just worried about whether I had air from the engine. Now, if I'm getting power from the electrical system to run my compressor, I better understand that what's happening to the electrical system because it's going to ripple to me. Fault propagation, false fault propagation in a lot of cases. False positives. We detect false alarm rate. That's the number that we get. But false positive, putting that check engine light always up on the dashboard for the pilot to look at and having nothing wrong with the airplane. It basically drives a maintenance action, puts you in delays and cancellation, and basically after a while, people don't even look at it. They lose confidence in your ability to tell them when something is wrong. And so it's like crying wolf. Sooner or later, you're going to have a real problem, and they're going to be ignoring it. So false alarm rate is one of the key things that happens that we have to mitigate. False negatives, worst problem. If I have a failure and I don't detect it, and I go flying with something that could be catastrophic, that's really bad. We will not allow that if we can prevent it. We would much rather have this than that. But this is not good either. And that's the economics part of it. Extra cost, extra weight, hardware, software, reliability of the stuff you put in the airplane to detect the faults that you're trying to prevent. And there is typically an unwritten rule that says the method for detection of a fault cannot exceed 10% of the item you're trying to detect. So if you've got 100 components, you better not have 10 components in the system that detects the faults. Anything over that, your reliability of the detection circuit rivals that of the system you're trying to.
How does that ratio work in terms of lines of code? 10% for the hardware, but what about the lines of code?
Well, Michael, you've hit on something that's really interesting. Fault detection and fault isolation and FMEAs and software are almost nil. I've done one in my life, an FMEA for software. It is a painstaking line-by-line code. And since software doesn't weigh cost, but it doesn't weigh, it's not really enforced at the software level right now. We don't do a lot of the bit software is 10% of the total code. In some cases, bit software is 50% of the code. And it's accepted because it doesn't add cost on a recurring basis. Doesn't affect efficiency of the airplane by adding weight. So let's take a quick look through history. What was it like in the beginning when you had all mechanical systems and you wanted to check the oil? You went out there, you pulled the dipstick, you looked at it. Who made the decision? The guy flying the airplane, right? Beautiful. Along came electronics, and now we can monitor that. So now we get the check engine light with a little oil on it. We go out, we still look at the dipstick. And who makes the decision? Pilot, driver still makes the decision. Get down to where we are today, which is right here, That's the guy doing the detection. There's no more dipstick. He's making all the decision. He has all of the sensors. You don't have any visibility to the system other than through that controller. Light's a light up in your cockpit. And a lot of times, that guy makes the decision whether it's safe or not. Okay? He will tell you about it, but he'll fix it if he can. And then going back further to autonomous, now remember, you don't have anybody in the loop. You've just targeted an airplane or a vehicle with a mission, and you go off and do it. So who's making the decision? Same controller. He's actually going to do the accommodation. And he might tell somebody downstream, but he doesn't have to. So we are getting into the point where we are getting closer and closer to not even knowing when faults occur because they're handled internally. The user of the equipment might not know that a fault occurred. He might not even know that there's a failure going on. And in an autonomous vehicle, who are you going to tell? There's nobody in the vehicle. So you have to do that. So the isolation and the detection becomes very critical as we get more integrated, more complex, and more autonomous. Okay, we're going to jump into the real reason why we're here, at least I am. We identify our hazard. We identify all the failure modes. Now what do we do about it? We do things called BIT. That's the detection mechanism, both hardware and software. Built-in test equipment. BIT detects and isolates. It does it throughout the flight, on the ground, in the air, transient in the garage, everything. BIT effectively sets the limit of how safe we are and how available we are, the quality of the bit that we do. There have been cases where first flights where the bit windows light up. And you don't know why, but the whole thing will light up because it's immature. You don't know. That's what we want to prevent. So bit, definition time, because they are very different. Built-in test. This is software and hardware that is used to detect faults and do isolation. So we measure things. All the things we measure for control, we put limits on to make sure that they're in control. Those are the bit software that checks those limits. Byte is anything, onboard or offboard, that is used to aid in detection of faults. Byte can be contained within the controller. You might have a valve, and you may have a sensor on the valve that says when the valve is open. That is byte if you don't have any other way of doing it. If you're not worried about it, but you're worried about when it's failed open, you have a sensor for that. That sensor, since it's not used for control, is byte. It's extra weight carried. Now you have to put extra hardware, extra wiring, and extra software. All right. We want to minimize that.
So what do the error codes represent? They're also part of the bit?
Error codes are bit. Yeah.
So, but they may not isolate. So we have both detection and isolation.
Well, the code you get back is usually the conglomeration of this is what failed, the fault in its location. That's the code that we get back.
Oh, really? Okay.
The maintenance code.
Sometimes you don't know.
Well, we never say we don't know. We say it's
I
to
know, it's
3
one
levels.
of the main things you could say. Yeah.
We cannot be, well, we had a fault, but we don't know where it is. We have to get to the 3 LRUs, so we'll identify the 3 LRUs. So if you think about a pyramid going in the other way, and what can be done, you have a bit pyramid. Maintenance bit, this is where you plug stuff into the airplane to try and detect what's wrong with it, right? It's kind of like an ODB scanner that you put in your car to find out what's wrong with your motor. Very useful, very thorough. It's like scanning a skin of an airplane to find out whether there are cracks. Very useful for an airplane, not so good if you're trying to fly the airplane. IBIT. IBIT is done on airplane. It could be flying, it could be on the ground, it could be in any mode you want, but it is initiated by the pilot in command. It puts the aircraft in a very specific state and does a very specific test for a very specific reason. So I could do an IBIT test that clamps the brakes to make sure I have braking force before I use it. Okay, that's a type of IBIT test. P-bit, when I power something on, just like your computer, it runs through a memory test. We always do the same kind of thing. So there are power-up tests. Do I have all my computer operating? Are all the voltages in place? Can I wiggle the valves? Can I output my controls? Can I monitor my input signal? That's P-bit. Then C-bit is the stuff that I do under normal operation that is done in the background typically. These are limit checks. These are rate checks. These are background RAM checks in computers. But these are things that are using the signals and my inherent knowledge of those signals to say they're good, they're bad, or I don't know. And this is where a lot of the problem occurs. Because when I'm looking at some signals and I'm looking at them in terms of their validity, it's in range, it's out of range, it's moving too fast, it's moving too slow. That's where I'll make some bit decisions that will light the light in the cockpit, to check engine light. But the problem is there's a lot of things that affect it. If I'm running a compressor off an electric motor and I get a momentary dip in the voltage at the electrical generation, I may slow the motor down. And if I'm expecting the motor to be within tolerance and I get a momentary lag in the motor performance because it dips down and that causes a pressure cycle, I may get a bit flag that says I have a failure in the motor or I have a fault in the motor. When it really isn't the motor, it was that I had a lag or I had a dip in the voltage at the electrical generation. Did the motor controller know? No. Did the electrical system care? No. So now I have a bit detection that is basically going to be a false alarm and a no fault found. So the interaction really kills me, and it really kills me down here. These I can control my situations a little bit more, so I can do individual isolatable tests. This one, I have to use only what's available. And that's where we start to fall down, because no one wants to carry extra hardware. Key points on this area is faults, you're never going to get rid of them. If I say nothing else, don't ever believe anything is going to last forever, because it doesn't. We build things to last 35,000 hours, 100,000 hours, 300,000 hours in some cases for small equipment. That's a really long time. Okay? They'll never get there. Now throw in software. Throw in cyber-physical systems where you're actually driving some of the mechanics with electronics. Throw in networks where the network glitch could actually cause you to read something incorrectly because you're not directly sensing it. You're sensing it from someone else who doesn't know whether it's in range or not. We have highly integrated, highly intelligent system. The system thinks it knows what's going on, but does it really? How much intelligence is actually built there? Again, we've reached pretty much a place where to increase our fault detection and isolation, we have to add sensors. Adding sensors is bad. They're unreliable, they're costly, they require power, they require software. Okay, so why do we do this? Because we get increased capability as we get more complex. You don't want to be flying around in a Sopwith Camel, right? We are getting to the point where complex systems matter. We need to move up in complexity because it adds functionality, it adds efficiency, but it adds complexity. All right? This is what you get when you have simplistic. Now, I'm going to question, which one is complex? It's actually the one on the right is a complex system. The one on the left is not. That gauge right there is very specific to a very single failure. And if it's in that red gauge, I know exactly what it is. Right? Now, if I wanted to add something, you have to shoehorn it in somewhere, and I have to add wiring. So inherently, it's less complex, but it's highly unreliable because I have a lot of connections. Go to a glass cockpit where you have 4 displays, all of them multifunction. It's kind of like you pull up a new window and get to the maintenance page, and pull up a new window and you get to the fuel system, you pull up a new window and you get to the valve. But it all depends on the network, it depends on the controller, and it depends on the software. So in terms of this took 3 people, maybe 4 people to fly, because you had to have somebody flying the airplane. You had to have someone looking at all the switches and gauges. This only needs 2 people to fly. And the rumor is someday that, there's the odd story that Boeing sometimes likes to say is, in the future there will be a pilot and a dog in the cockpit. And the purpose of the pilot is to feed the dog, and the purpose of the dog is to bite the pilot if he touches anything. Whether we actually get there or not is to be seen.
Question: are those displays or glasses, just purely windows?
Those are these are windows. These are the CRT displays. We do have lots of switches still, but typically all the maintenance and all the information comes through the displays. Typical example: conventional airplane. Probably the ones that, if anybody flown in the last 10 years, this is what the electrical system looked like. 3 sources of power, add a battery, add something called a ram air turbine, you get 5. You have 3 power buses, 9 power connectors, 4 processors, less than 200 kilowatts of total electrical energy for the airplane. 496 states. I can test every one of those in my lifetime. Very easily done, and we did it. Move to the more electric airplane, where electricity becomes the driving factor for safety and functionality. Have 7 sources, 12 buses, 30 contactors. All right, I have 10 plus processors, and that's actually pretty low. A megawatt of energy on the airplane. I have, over 1 billion possibilities of configurations. Not all of them can be realized, of course, but many hundreds of millions to go through. I can't test that in my life. I have to be able to do something else. That's a problem. Detecting the types of problems associated with these different billion states is another problem. Because how much can I put in software and hardware to detect all those different states? And what do they mean? In state 350,429,000, is that bad or is that good? Becomes problematic. So why do I do this? Because when I get complex, I get better safety. I get more efficient maintenance if I do things right. I have shorter downtime. If I can isolate to the particular component, I can replace it quickly and get you back in the air. I want lower false alarm rate. More than anything, I want lower false alarm rate, and I want better results from actual faults. These 2 things, longer availability and longer time on wing, these are a function of accommodation. When I can figure out what the fault is, isolate it, and figure out a way to continue to fly with that fault, that's accommodation. I don't want to get into that because that talks about redundancy, pseudo-redundancy, shutdowns, and load sharing and all of that stuff. We're not going to get there. So where do we need to be? Minimize bite. You probably see that on every slide following. That is key. We don't want to carry equipment around for no reason. They won't let us in a lot of cases. So what do we need? We need better bit. I-bit, C-bit, and P-bit algorithms and methods, tools. Why? Because we don't have the visibility that we used to have. The systems are so complex. Things that are happening at the other end of the airplane may be affecting me if we're an interconnected organism, and that's really what an airplane is today. We need to understand the relationships. Right now, we directly measure. We can't do a lot of inference because a lot of times it's not accurate enough. So we need to get there. We need to do a better job at false alarm rate. Right now, papers in the world, scholarly papers say the false alarm rate for avionics is above 50%. Okay, think about that. Half the things that show up on the pilot that's going to cause you to miss your flight is false.
It's getting worse then. The number I knew was 40%.
It's actually maybe even as high as 80 in some cases. No fault found. That's an economic issue for both the airlines and for us. Because now, if you do get something failed, you have to carry the spare around with you to replace it if you need it. Then when you get it, you got to send it back to the manufacturer, me, and I'm going to put it on my test equipment, and I'm going to say it's perfectly good. You pulled it off for no reason. Well, we pulled it off because I said it was bad. So I have to be able to do a much better job of doing the isolation so that I don't get equipment back that's actually good. How do I do this? We have to have some way of learning how the system operates, what's normal and what's not. We have to understand what detection is happening while we're in control. And that's control at the top level, not just at my low regulatory control, but at the supervisory level and at the system level also. Model-based detection and isolation. That's another good way. If we know what the models will look like, we know what the system interaction is, we can predict what the effect might be. We need those types of tools. How do we get there? Here's our challenge. Limited computational resources. That little gold box is not as powerful as your laptop. Typical laptop, 4 cores, unlimited storage, 16 gigs, 3 gig processor. What do we run with? Single core, 4 megabits of ROM space, maybe up to 256K of RAM, and 600 megahertz. That's the computational engine that's flying around on the new airplanes for the controls. Not a lot. And if you try and put 3 million lines of code into that thing, it's not going to like it, especially if it's all for bid, right? The workforce that we work with is not as highly educated as we would like it to be in some cases. We have very good technical skills that are very good at designing systems. But these things that we need are going to come from theory and from advanced methods. That's not our day job, okay? Our day job is to produce the hardware. We depend on other people to give us the methods and the tools. We didn't develop compilers. We didn't develop modeling technology. We use them. So we need that skill set. We need that tools. We need to get things that don't necessarily like each other, mechanical and electrical, and software. God, we can't even get them in the same room together. But we have to start treating them as a system. We can't isolate one from the other and say, I can detect mechanical, I can't detect electrical. We can't do that anymore. And we have to go to basically a model-based detection where we can do some of that. And I'm pointing right now at what Kyle and George have done in a heat exchanger file. I know there's other work being done from UConn in the AMS for optimal sensor placement. That's also key to helping us get there. But this is where we need to be. This is what needs to be attacked. Another
Question.
Yeah.
Why computation power still limited?
Because,
Like Boeing 787.
well, because of location. One of the big drivers for reliability is the number of solder joints. I technically cannot put a ball grid array on a piece of avionics that has heat cycles on it. They will not last 100,000 hours. If we're lucky, we'll get 3,000 hours out of it. I can't put multi-core because I don't know how to certify a multi-core system, because I don't know how the resources are managed in a deterministic way so that I can guarantee that the control that I'm running, critical control, is not going to be preempted by the other processor who's doing a background task. That's why we're not there. There's an effort here at UConn, also with UTAS, about trying to get multi-core certifiable. What do we need? Right now, we're not even allowed that. If you talk to one of our customers, they don't even let us turn on the cache because it's non-deterministic. DMA is turned off because you never know if you're going to write to the wrong areas. So we take our big, 3.2 gig or big 600 meg processor that can do, multi megaflops and reduce it down to K flops because of all the things we turn off because they're not deterministic. Okay, this is another commercial for UTAS. This is what we call the fly sheet. This is the airplanes we're on up until 2010. We're on almost everything that flies. Any airplane, new, old, or even in the future, UTAS will have something on it. UTC will have something on it. So it's a big deal for us. We need to get this done. So where is it going to come from? Industry? We are doing what we can. We do have some limited resources in terms of day jobs to go and investigate how to do built-in tests. We have some capability there, but not nearly what academia, partnerships with industry and government. These are the things that are going to drive the next generation of bit detection and bit isolation. We don't have the capability, we don't have the time to do this, right? We're going to be looking at the Institute, right? The Institute here is uniquely placed. You're tied in with UTC. This is what we're looking for. This is the kind of thing that we're spending our time trying to get people to get interested in. It affects us every day. Everybody's looking at this. This is one of the big annoyances in the aircraft world is isolation detection. That's it. Questions, comments? Yes?
What are the industry's favorite algorithms for fault detection and diagnosis?
Excuse me?
What are the industry's favorite algorithms for this purpose?
Algorithms? There are fault detection. Typically, I'll give you my opinion what the favorite algorithm is. It's out of range and rate detection are typically the algorithms we use for fault detection.
Out of range and what?
Out of range and rate of change. So we can detect when something is moving slowly and all of a sudden it ramps up and it changes by a large amount in a certain amount of time. That's bad. It should not have done that. Valve movement can't go from 0 to 100% in a single cycle. Those types of things are typically what we use at the control bit, at the C bit level. IBit is cycling. We will run scenarios, and typically we're limited on time. So what we'll do is we'll cycle, for example, the valves on an air management system. We'll cycle all the valves. We'll see that we can control them. We'll measure the time, and we'll measure the position. Great. So now we know that the valve works according to the schedule that we expect, and that can tell us whether we expect it to work. Now, that worked today. That worked at the beginning of the flight. That doesn't mean that an hour later something doesn't clog the valve and stop it. But at the time of takeoff, we were good to go. So what do we do when we can't cycle the valve because that would put the airplane in a compromised condition? We do continuous bit. The valve should be here. It's not. Therefore, we think it's a fault. A, is it the sensor? Is it the valve? Is it something else? But typically, it's rate of change, and limit checks. Yes?
I really like the presentation. My problem is, what if you have something wrong with your BITE? Do you have BITE to test BITE?
That's why we only allow 10% of the circuitry to be byte, because you have to prove the reliability of the byte to be better than what you're testing. Yet that ambiguity group that you get with 10% of byte is something you have to live with. Okay? You don't do byte on byte. Okay?
Extending from that, from that 10%, you talk about the need to minimize byte. What kind of analysis is done on that? Because byte significantly affects your bit. Like the more information you have on your system, the better your bit will be. So,
but the difference between byte and bit is if I have a lot of information in the system that I need for control and I use it more efficiently, I get better bit. It's where I don't have visibility into the system that I have to add visibility for not for control purposes, but just for built-in test for fault detection. Did I answer your question, Billy?
I guess somewhat, but so I'm assuming there has to be some balance between byte. Whereas the more byte you have, the better your bit will be, the more accurate your bit will be.
Correct.
Right.
It has to be a trade-off.
And
right.
I add byte for critical failures where I can't do it.
So
Hazards.
you have a byte that actually reduces the reliability for all systems.
Yeah. Okay, I was sorry.
Go first.
Okay.
Okay, I was going to ask, what's a more common issue that you have to set a bit for? Is it typically faults that happen in the system, electronic faults, or is sorry, switch that. Is it faults that occur in the physical system, or like more sensor-based faults?
Historically, it's all been in the system, but now we're reaching the point where it's moving. It's moving toward the center. It's not totally there yet, but we are seeing faults that are unrelated to my system that show up on my system's fault log, and it's due to somebody else causing it. Because I didn't understand that in the case of an electric system, I lost power for 100 milliseconds, and therefore I couldn't move the valve during that time, and I flagged it as a valve problem. I didn't know that I lost power. That kind of thing, it's moving that way, but that's where we're really shaky right now. Michael?
So you talked about the preferred algorithms, if you will, for detecting faults, and that's really applicable at the lowest level of abstraction. If you think at the higher levels of abstraction in the system, what is your thoughts and vision on the use of model-based approaches for fault detection and isolation?
It is the way, to me, it's the wave of the future.
So maybe you want to elaborate on that for the group, because.
Okay. One of the things that we have available to us now is behavioral models and functional models of some of the systems that we build. And even with our limited capability, we can carry them, simplified models aloft, so that we can actually make some decisions based on what the model says the inputs and the outputs should look like for a given state and what the actual inputs and outputs are. And with that difference, we get a much better indication of what might be going wrong. And we can do that in some systems pretty accurately. And it's used for fault isolation, especially when you have dual redundant systems. And if one channel is lying to you and the other one is telling you the truth, you really don't know which one it is. The model's the referee. The model says the value should be 3. One is telling you it's 5. The other one's saying it's 3.5. You now know who to believe. So models can play tiebreaker in redundant systems. They can also give you what the expected envelope is of the answer you're looking for. So that's how we're going to use models. The problem is getting the models complete enough so that the interaction between the two subsystems is accurate enough to do that prediction.
One last question? Oh, one. We're out of time, but maybe take two more questions, and then we can stay later and talk informally because people might have places to go. So 2 more questions. You good? I think good.
In the scenario that you talked about where the mechanical system experiences a dip in the electrical power and the electrical system doesn't really care, you had made a comment about how it didn't really register the fault on its output. Do you guys utilize interface specifications? I understand it could be 2 different companies, one doing the electrical system, one doing the mechanical system. An interface specification that states that we'll need this kind of information to analyze faults, which would kind of be signed off on both entities. Is that something that you guys utilize?
Oh, absolutely. ICDs and specifications for that are something that we utilize across the system. Typically, when systems are designed, that interface control document is flowed to the 2 separate companies and controlled by the central. But that information is there. The question is, I expect the power to dip, but when do I know? Because if I get a dip in electrical power and I have a confirmation time of a second, I'm not going to take action until a second has occurred because that's normal operation. And my motor drive for my captive system is going to flag a fault at a half a second.
Right.
That's a problem. Now, the time nature of that is potentially something that is not shared in the ICD. We do start now with the big networks and the backbones and the airplanes trying to get more information, but there's a ton of information that we can share. 90% of it is useless, 10% is good, and it's temporal in nature. So we have to be able to do that. And that's where a lot of this interrelationship, I have to know certain things. Maybe now I have to monitor my own voltage. I never had to before. Maybe now I have to do it.
I believe you have a global reasoning system that looks at across multiple things.
And I have to do it in a time frame that doesn't allow the faults to propagate or to occur so that I have failure modes, right? One of the things I didn't talk about is confirmation time. Just because I get a blip on a sensor doesn't mean I cause a fault. It has to be there for a particular amount of time. That time is very important because that tells me what my false alarm rate. If it's hard over, it's going to stay there. If it's transient, it may recover and I won't even flag it. If it's intermittent, I have to make sure I understand what the intermittency is. Bad wire and bad sensor, bad connector, whatever. those types of temporal things are really a lot of times what cause the false alarm rates.
It's a local thing is the problem here.
Yeah.
Because individual people just build their
So
own thing.
I think our webcast would be ending too if it did come on board. I know there are so many questions. It was such an interesting presentation. We'll be here for the next 5-10 minutes.
As long as I
so if you have any questions, we can talk informally. So I just want to formally close it. Thank you to all of you for coming, participating, asking really good questions. And thank you, Rich, for coming, taking time out of your busy schedule. Sure. There's a little token of appreciation for you.
Thank you. My pleasure.